How long did that? Oh. We give them some CV for time to time. For today.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everybody. How's everyone doing today? Good. It's yeah, no stress. That's getting stressful. I know. I appreciate you guys being. I always appreciate that you guys come to class. You know, I think one thing I've noticed over the last couple of years that because of the recordings and stuff that the attendance seems to wane at a certain point, which I totally understand. But I'm very glad if you guys come into class, especially when you guys are kind of busy with that. So thank you for that. All right. So the plan for today is we're going to finish up our lecture notes on lower extremity biomechanics, and so I have a couple more examples to do together with you guys, and then we're going to talk about injuries. And so I don't think it's going to be too much. We may end a little bit early, and then that's totally fine. We'll just end kind of when we'll end. So today is the cutoff, and so the midterm exam is a week from today. And so everything after today will not be on the midterm. So everything today is kind of the last day of content that we've covered. Expect you guys to know for the midterm. All right. So today, this afternoon, I did post the midterm exam from a year ago. So that's on Canvas for you guys to look at for some extra practice. I'm working on kind of doing some extra practice problems because I know we talked about that last time. But I'm hoping to have that posted. I'm probably going to work on it today. Office hours is not showing. And so if I have some time today, then I'll try to post it before I go. But if not, then by tomorrow for sure, I'll have some extra practice problems for you guys too. Okay. All right. And so just some reminders for the midterm exam. Remember, it's going to take place in class, and so there are no plans to offer the exam virtually. So want to be here in the class. In terms of what you can bring your writing utensil, you can bring your calculator. You can have one sheet of notes, and so it's a 8.5 by 11 sheet. You can write on both sides. You can write it. You can type it. Whatever you feel most comfortable with. And kind of just like we talked about last time, that's the first thing that you should guys be doing when preparing your sheet of notes, when you're doing your studying, is to look at the study guide. So definitely check out the study guide. The study guide is posted on the week 6 page of the Canvas. Okay, and that's where you can find kind of the past pictures. All right. And then besides that, there's one more homework. So homework 3, remember, is due on Monday. And so it's just some additional practice problems with the lower extremity stuff, and so some additional kind of static analysis problems, as well as a few kind of conceptual questions on the lower extremity. Okay. All right, I think that's all my announcements. Quite a lot of announcements here. Are there any questions about the midterm or anything coming up that I can answer before we get started? Okay. All right, so let's go ahead and get started. And so let me go ahead and bring it back to the iPad here. Okay. And so we're going to continue on with lower extremity biomechanics. So last time when we were here, we did 2 examples, mostly having to do with the hip joint. In particular, in terms of what kinds of stresses and what kinds of forces that the hip muscles have to exert in order just for you to get up straight. Okay, and so we're going to move a little bit downwards today. And so we're going to do one example at the knee, and then one example at the okay. This example, static analysis at So the knee has two primary muscles that act on, and primarily the knee joint is essentially a hinge joint. There's a little bit of rotation, a little bit of adduction, but its primary motion is that it acts as a hinge. And just to kind of remind you what that means is that, when you have a hinge joint, there are two kind of primary motions that we associate with hinge joints. So there's flexion, in which the knee joint kind of, becomes more, or the angle of the knee becomes less, and then there's extension where, the knee is straight to go. So if I were to draw kind of a knee joint here. So this little dot right here, this is the knee joint. So in this figure here, this kind of upper segment here is going to be your thigh. This is your lower leg. This is, so kind of imagine this is kind of the configuration you would be in if you're kind of sitting down in a chair and your leg is kind of hanging on. Okay. All right. And so the two primary motions, and so the nice thing about a hinge joint is that we can draw it kind of quite easily in a 2D plane. And so there's no out of plane motion. Okay. And so when you flex at the knee joint, it means the lower leg is going to brought up in this direction here. For flexion, you're kind of bringing your lower leg back into your thigh, so we call that knee flexion. But then if your knee rotates or if your lower leg rotates the other way, we call this extension. Okay, so flexion and extension. And the other nice thing about the knee joint is that we have kind of very clearly defined muscles that produce these kinds of motion. Okay? So flexion at the knee is primarily produced by the hamstring muscles. And so the hamstring muscles are kind of this muscle that kind of exists on the bottom of the knee. Okay. So the muscle fibers kind of run like that, and they kind of attach kind of onto the back of your lower leg. This would be the hamstrings. And then we have extension at the knee. So the extension at the knee is produced by the muscle on the front of your thigh, which is your quadriceps muscle. Quadricep muscle kind of has fibers that kind of run like this, and then it kind of extends over the patella. And so remember, the patella is your knee joint. So we'll talk about kind of the significance of that. Okay. So that is your quadriceps. Okay. All right, and as you can imagine, both the hamstring and the quadricep muscles are very crucial to walking. And so whenever you take a step, the main muscles that kind of produce a lot of this force is your hamstring and your quadriceps. Your calves do as well. And we'll talk about the calves in a second. Okay. So these are two kind of very important muscles in your body. Okay. But the other thing that we have to know about the knee, kind of very similar to the hip, is that it plays a big role in kind of bearing the weight of your body. in fact, there's a lot of soft tissue within the knee. We have all your ligaments, the MCL, PCL, ACL, LCL, all and the meniscus. So all of these are kind of in support of the weight bearing capabilities. Okay. So your knee is a very essential joint, and if you hurt your knee, it can really kind of hinder your mobility and hinder your quality of life. Okay. So the example we're going to do, we're going to do a fairly simple example, and so we're going to compute the biomechanics of someone doing a leg raise exercise. So let me go ahead and draw the geometry for that. Right, and so for this example, we're gonna, imagine that we're kind of raising our leg, and so for those of you who are sitting down, if you kind of extend your knee forwards, that's considered a leg raise exercise. And so the motion that we're going to be basically imagining is a knee extension going this way. Okay, and so that means the muscle that we're going to be looking at is the quadriceps muscle. So the quadriceps muscle, we're going to assume acts like this. And so this FM here is the quadriceps muscle force. Okay. Go ahead and just draw kind of the center line of your lower leg, and we'll go ahead and define this angle here. So we'll say this angle here is theta m. Okay. And so the attachment angle for the quadriceps muscle, we'll assume is no, just like we usually do. Okay. And then resisting this motion or resisting the muscle forces, we have some weights. Okay. So typically, when you do a leg raise exercise, if you're doing it to work out, one way that you can kind of increase the load is that you kind of apply some weights on your feet. And so that either comes in the form of ankle weights, or I've seen people even tie like some big weights at the gym to their feet. Okay. So we're going to assume that we have kind of a big weight here at the end. So we'll call that W. And we can even include the weight of your feet and your shoes in that number as well. Okay. So we'll assume all of those kind of act at the same place. And then we're also going to consider the weight of your lower leg as well in these applications. Okay, so we have W leg that's acting just like that. Okay. And so to kind of complete all the information that we need for this problem, we need the angle here. Okay. And so we're going to assume that at the current position, the leg is angled at an angle of theta with respect to the horizontal. Okay, so we're going to find theta just like that. And then in addition to that, we have all the distances between the knee joint and the respective forces. Lm, muscle force. We'll call this LL. So that's the distance along the leg of where the weight of the leg is acting from the knee joint. And we'll call this last length LW. Okay. So that's the total length of the lower leg, which is the distance along the leg where the external force is being applied. All right, and then finally, of course, we have to include the joint reaction forces, and so we need some joint reactions here. And so we'll call it JX and JY. And so just like we normally do in these examples, we're going to compute. We're going to compute the magnitude of the muscle force. Joint reaction. All right, so a pretty standard problem, and actually, in fact, this problem right here, at least in terms of its geometry, is not too different from the homework problem. And so, and I'm talking about the previous homework problem, because in the last homework I got a lot of questions in terms of how do you actually compute the angles, how do you incorporate that into the joint reaction force. I think a lot of people kind of have some trouble with that. So hopefully this example will be kind of helpful. Because in this example, I'm going to kind of describe how you would, or at least the logic that I typically follow in terms of computing the angles. And we'll talk about kind of a few finer points. Okay. All right. So luckily, we have just enough unknowns, and so just kind of always remember that whenever you're doing these problems, you get three kind of governing equations, and so you have some of the forces in the x and y direction, as well as the sum of the moments. Okay. Okay, so let's go ahead and write out those expressions. All right. So we have the sum of the forces in the x direction. Okay. All right. So we have the sum of the forces in the x direction. So we have only two x direction forces here. Okay. And so we have Jx, which is the joint reaction force in the x direction. And then if you look at the two other the two weights that we have here, the weight of the leg and the weight at the end, the external weight, those are only acting in the y direction. So these don't make any contributions to the x equation. Okay. And so that's one thing about gravity forces, about any kind of weights, is that we always assume they're always going to be vertically upwards and vertically downwards. Okay. And so when you're summing the forces in the x direction, almost never you're going to have any. And that's true even if your limb is angled to a certain degree. So if your limb is angled, the tempting thing to do is kind of say that we know that the leg is kind of angled this way. Maybe the weight kind of goes that way as well, but you always assume the weight goes kind of vertically upwards. And so the only two contributions to the x force are going to be from the joint reaction force in the x direction as well as Fm. Okay. And so based on this figure right here, we can see that Fm, it's a little bit hard to tell, it's kind of the way that I drew it. But we're going to assume that this Fm kind of points to the left. So we're going to have a minus sign here. Okay. And then, of course, we need to take the horizontal component of Fm as well. So the horizontal component, most of the time, we're going to take a cosine. Okay. And then the question is, what angle do we put inside this cosine? Okay. So let me actually draw another figure here. So I'm going to draw the kind of the leg just by itself. Okay. So this line that I've drawn here is the leg, and so this is going to be theta we have above. Okay. And then I'm going to draw Fm, a little exaggerated, just like that. But we know that Fm makes an angle of theta m relative to that leg. Okay. Okay. I'm going to take this figure. I'm going to take Fm, and I'm going to draw it kind of over here. Okay. So Fm we know is kind of like this. Okay. And then let me draw these two components as well. Because in order to sum the forces in the x direction, we need the component of Fm in that x direction. And eventually we're going to need the y component as well. All right. And so of course the angle in question here is this one right here. And so the question is kind of what that angle is, right? Remember, whenever you use an angle inside a force balance equation, right? This angle here, this angle should always be relative to the horizontal. Or in other words, whatever angle that you're summing the forces around. Okay. In other words, the angle should be defined relative to the horizontal. Remember what an angle represents. An angle is kind of just a rotation from one orientation to another. Okay. And so if we look at theta m right here, at least the way that it's defined, theta m is a rotation, but it's not relative to the horizontal, right? So this theta m here is defined relative to the orientation of the leg. And so if you took this force balance and you just used the angle theta m, okay, this wouldn't be quite correct because that theta m isn't defined relative to the horizontal. Okay? And so what you would need to do is to say, okay, I know the leg is angled with respect to the horizontal. I need to add that angle together with this angle in order to get the right. Okay. And so we can see at the bottom here that the leg is angled with or is oriented with an angle theta with respect to the horizontal. Okay. And so the correct angle here to use in this equation is not going to be theta m. It's not just theta, but it's going to be theta m plus theta. Okay, because it's going to be the sum of the two angles. And so another way that I like to think about it is you can almost think of it kind of like the rotations of a clock hand. Okay? And so if we start a clock hand kind of pointed horizontally kind of to the left right here. Okay? I find this kind of easy to visualize from here, kind of what angles we need to rotate in order to get into that final configuration. Okay, so starting from here, the first rotation, we rotate counterclockwise upwards by an angle of theta, okay? And so by rotating an angle of theta, we know that this vector right here is in the same orientation as the leg. And then from the orientation of the leg, we rotate counterclockwise a little bit more in order to get into the orientation for FM, okay? And so this right here, this final vector is the orientation of Fn. And so hopefully from that figure, you can see that the total angle that the Fn vector has with respect to the horizontal is the sum of theta and theta m, because we have to rotate through both of them to get to that final orientation. Okay. Any questions on this? All right, and so I've told several people in the class. I think this part of static biomechanical analysis, it's hopefully it's not the most difficult thing in the world. I think you guys have been doing force balances for years now. But I think what makes it challenging is just the geometry, the trigonometry of everything. So and I think just very quickly it's very easy to kind of get overwhelmed and kind of with all the different rotations and stuff. And so when you're doing these problems, even though I know it's kind of a pain, really take the time to kind of draw out kind of the image, draw out all the vectors. And so I think that way it's a lot easier for you to kind of visualize, see kind of what's going on and use the correct angles in your okay, so that's the X balance equation. So let's take a look at the Y balance equation. So this is going to look similar. And we have the joint reaction force in the Y direction. We have the vertical component of Fm, to Fm, sine of theta plus theta m. Okay. And we use the plus sign here because just visually what we can see is that Fm is pointing upwards. And so we put the sign as plus there. And then we subtract our two weights. Okay, minus W leg and minus W. All right, and then finally we have some of the moments around the knee joint. Okay, and we have three contributions here. Okay. And so remember, because we're summing the moments around the knee joint, we don't get any contributions to the moment from JX and JY. And so we only have contributions from the moments from the forces that are acting kind of away from that. Okay. So first we have the moment from the muscle force. And so for the muscle force, we have FM, LM, sine of theta M. Okay. This is a positive moment because that muscle force is going to pull, is going to cause a counterclockwise rotation about the knee joint. We have the moment from the weight of the leg, and so the weight of the leg is a vertical force, and so we multiply it by the horizontal distance between the weight vector and the knee joint, and so that's LL cosine theta. And then we have a very similar expression for the weight at the end, so W LW cosine of theta, and it's all equal to 0. So those are our balance equations. Okay. And so of course, what we can do here is we can go ahead and solve. Right. So we have all the equations that we need. And so where we're going to start is let's start with the moment equation. We only have one unknown here. And so if you perform the algebra, what you get is this. So FM is equal to W leg L plus W. Both these are multiplied by cosine theta. And they're going to be divided by the moment arm for the muscle force, which is LM sine theta. All right, let's plug in some numbers just for fun, just so you can kind of see, some typical numbers. So some typical numbers for this, let's say the weight of the leg, 50 newtons. The external weight, we'll say is 50 newtons. Weight M, we'll say is 15 degrees. Data, we'll say is 45 degrees. And we have the various length. And so we'll say LM here is 12 centimeters. LL, 2 centimeters. W. And so if you plug all those numbers in, and you just punch into a calculator, what you get is FM equal to 1958. All right, so once again, you can see that the amount of force that your muscles are exerting is far greater than any kind of external force that you're applying. Okay, And that's primarily just due to the fact that your muscle attachment length is usually quite small in relation to weight. Okay. All right, any questions on how we obtained that result there? Yes.
Can you repeat the step for FM? How you calculate the distance for?
You mean this LM sine theta here?
Yeah.
Okay, yeah. And so remember this FM, when you're computing the moment, you want to compute the moment arm for that force. And so there's a few ways that you can do it. So let's assume here that we have the knee joint right here. You have the muscle force. We know that this distance right here is. Okay. And so the way to kind of compute this is or the way I always think about it is to kind of use the information that's given to us in the problem, right? So we have this distance, and so we have LM. So this LM is kind of the distance along the leg between the knee joint. If we were to draw kind of a line that's perpendicular to this, perpendicular to the leg, the perpendicular direction would be kind of like that. And so one thing that we know about the moment arms is that if you compute the perpendicular distance, which is kind of the shortest distance between the vector and the joint, that is exactly the moment. Okay. And so if we were to find the component of the force in this direction, then if we multiply it by LM, that would be the moment from FM. All right, so we want to compute the component of FM that's perpendicular to the leg. And so luckily we have the perfect angle for that. And so remember, theta M here is the angle that FM makes relative to the leg. And so we kind of draw a triangle here. We're going to draw like this. And so to get the perpendicular component of FM relative to the leg, we take FM sine theta. And so that would give us the force in this direction. So this would be FM sine theta M. And then we multiply it by the moment arm, which is LM, and that's how we get that moment. Any other questions on this result here? Okay. All right, let's take a look at this equation here. So I solved this using variables kind of for very specific reasons, and that is to kind of examine the effect of this attachment. And so we've talked about the attachment angle before, but based on where it is in the equation there, you can almost think of the attachment angle as kind of a measure of mechanical advantage. Okay? Right? And so the amount of force that your muscle has to exert has a strong dependence on that attachment. And in fact, because we have sine of the attachment angle in the bottom, right? The greater the attachment angle, the less force the muscle has to apply. And to kind of illustrate this, we can actually quad it. And so the extreme for the attachment angle is 90 degrees, and so you don't really see any attachment angles greater than that. The minimum is 0 degrees. And so essentially here we're making a plot of 1 over sine theta. And so actually, you know, we have kind of a, you know, if you actually plot it, it kind of looks something like this. Okay. And so at an attachment angle of 0 degrees, actually, you know, technically the amount of force shooting is infinite. Although it's never actually, you know, 0 degrees. But you know, you can see here the greater the angle, well, actually FM, the greater the angle, you know, you can almost think about the greater the angle, the more mechanical advantage your muscle force has. I know it's not the exact definition of mechanical advantage, but it kind of has that same kind of connotation of like, you know, the greater the attachment angle, the less work. All right. And the interesting thing and the fascinating thing is that your body knows this. And so, you know, on your knee, you have a very kind of, you know, strange, it's kind of a strange bone when you kind of think about it. You know, there's not very many bones like this in your body, but your patella bone, your kneecap, actually helps to increase the attachment. And so if you actually look at kind of a cross section of someone's knee, you know, the tendon that actually attaches the quadricep muscles to your lower leg actually wraps around the patella. Okay. So it looks kind of something like this. So we have kind of patella. And so we're looking at kind of a side view of the knee. Okay. Oops. Okay. And if we draw kind of the tibia, so we'll assume the tibia looks something like this. All right, and so because the quadriceps muscle, you know, the quadricep muscle kind of mostly kind of exists kind of over here. Okay. But then to attach to the tibia, you know, what the tendon has to do is it kind of have to wrap over the top of the patella. Okay. And of course, this is kind of a very crude drawing of it. And then the attachment angle, or at least the one that we use for calculations, is right here. So that's theta m. And so because the quadriceps tendon has to wrap over the patella, you know, it actually, you know, that's kind of a nice kind of side effect of having it there is that, you know, that attachment angle just purely on the geometry, you know, that assists your quadricep muscles quite a bit. And so it doesn't have to work nearly as hard, you know, when the patella is there. But then that kind of brings up an interesting point where, you know, there's some people that either have an injured patella or some people that, you know, have a very kind of small patella. And so for those people, you know, their quadricep muscle has to work just a little bit harder because, you know, the attachment angle isn't as high as it could be. Okay. All right, so kind of a very kind of interesting kind of thing stuff. Yeah, I think most people associate the patella as just kind of like just a protective cap. but it also kind of helps your muscles as well. All right, any questions on this? Okay, all right, so let's go ahead and move on to the ankle. So this is the last joint that we'll cover. All right, so your ankle joint is one that's actually very fascinating. It's very interesting. And so, primarily, we think of it as kind of the articulation between the fibula and your tarsus, which are your feet bones. But your tibia actually plays a role in it as well. So you actually have quite a few bones there, and kind of very similar to the knee joint. These bones just don't really naturally kind of all fit together. Okay. And so it's quite different from the hip joint, where the hip joint just fits so naturally into your pelvic bone. That's not necessarily the case with the ankle. Okay. And so to hold it all together, very similar to the knee, your ankle consists of a lot of very strong, ligaments and tendons, and relies on a lot of those for stability. And so because of that, ankle injuries are quite common, and so probably everyone's sprained their ankle at least. All right, and so when you look at motion at the ankle, it actually is quite complex as well. And so we have hinge-like motions, and so we have plantar flexion, dorsiflexion, and so that's very much just like your flexion and extension. But your ankle is also capable of varus and valgus motion as well. So it's not quite a ball and socket joint, but it has some kind of characteristics. Okay. And there's one other motion, also eversion and inversion as well. Because when you kind of and on the side of your it's quite a flexible joint. So there's a lot that you can do with your feet. The primary motions, at least for most people on a day-to-day basis, are plantar flexion and dorsiflexion. These are the motions that are associated with So the example that we're going to do actually is a foot that's under plantar flexion. All right, so plantar flexion, the main muscle that's associated with this is your calf muscle. We're going to draw kind of the a diagram of the foot, like this. You're looking foot. Okay. And so the calf muscle is the muscle that's on the back of your foot, and so it attaches primarily at your heel. Okay. And so we're going to say we have a muscle force going in this direction. Okay. And we'll say that we have a muscle force stated M that's acting right there. Okay. Kind of similar as the the hip joint. We're going to assume the ankle joint is kind of offset from there. Okay. And so this little dot right here is the ankle joint. And actually, let me draw it kind of more in line with FM. Okay. The X in the Y direction, or JY in the Y direction, the X in the X direction. Okay. And then the primary external force that we're going to consider here is going to come from the. Okay. And so as this person kind of plantar flexes into the ground, right? So they're going to kind of drive their toes into the ground, which is what happens when you take a step. There's going to be a normal force that kind of comes out from the ground. Maybe something like this. Okay. And we'll assume for now that normal force, as this person takes a step, okay, is going to be the entire weight of the person's body. So we're going to have a value of W. All right. So let's look at geometric dimensions. Okay. And so we'll assume that the horizontal distance between the normal force and the ankle joint, we'll call that LW. Okay. And then we're going to assume that the FM and the ankle joint are kind of on the same horizontal plane. And then the distance between them, we'll say is LM. Okay. And so just like we normally do, we can, let's go ahead and solve for the muscle force and the joint reaction forces. Okay. All right, so another kind of pretty standard problem here. The geometry here isn't too complicated. The only thing we just have to be careful of is the way that theta M is defined. Is going to be going to make our calculations a little bit different. All right, so let's start with the moment equation. Actually, we're going to sum the moments around the ankle joint. And so the first thing that we have here is the weight, okay, or the normal force. And so we have the weight. We're already given the horizontal distance between the weight and the joint, and so we can just multiply this by LW. Okay. And we know from the figure here that normal force is going to produce a counterclockwise moment around the joint. Okay, so that's why we give it a positive sign. And then the muscle force is going to oppose this, and so we have FM, LM, okay, But instead of sine of theta m, we're going to use cosine theta m instead. And so the reason for that is kind of the difference in the way that theta m is defined. So theta m is defined relative to the vertical line as opposed to the horizontal line. Okay. And so if you want that component of the muscle force that's perpendicular to the LM, then you can take cosine of that angle instead of sine. All right. And so we can solve this equation for Fm. And so solving this equation for Fm is fairly simple. Fm is equal to W, LW divided by Lm cosine theta m. Okay. And so we plug in some numbers for this. And so let's say that we have, we'll say W is equal to 300 newtons. We'll say that LW here is 5 centimeters. We'll say that theta m 30 degrees. We'll say that LM is 3 centimeters. Okay. And so we plug all those in and we get Fm is equal to 577.35 newtons. And so now we can take that muscle force, we can plug it in and solve for the joint reaction. Okay. All right, so we sum the forces in the x direction. We only have two here, so we have Fm sine theta m plus Jx equal to 0. We solve this equation for Jx, so we get Jx is equal to minus 288.68 newtons. Notice how we got a negative answer for Jx, and so all that means is that the Jx is actually pointing in the opposite direction of what we drew. Okay, so the Jx is actually pointing to the left. Okay, and then we sum the forces in the y direction, and so in the y direction we have Fm cosine theta m plus Jy plus W is equal to 0. We solve this equation for Jy. Jy is equal to minus 800. Again, we get a negative result, and all that means is that we are Jy is in the direction opposite of, should be pointing downwards. Right. Any questions on this example here? All right, and so for the last 20 minutes of class today, let's talk about some common injuries of the lower extremity. Okay, so let me go ahead and bring back the PowerPoint slides here. Okay, and so we're going to go from the hip downwards, and so we'll talk about some common injuries that can occur and kind of why they occur. And so we'll start at the hip. So the hip joint, like I've mentioned kind of many times in this class, is a very quite a stable joint. But even for stable joints, you can still have some susceptible to injuries. Okay, and this is especially true for elderly people who is more susceptible to things like osteoporosis or kind of degenerative bone disease. And of course, those who play kind of active sports, contact sports, they're more susceptible to injuries as well. Okay. So let's talk about fractures first. So fractures, the most common place for fractures to occur at the hip is going to be at the femoral neck. So kind of the thin part of the femur, kind of right where kind of the head attaches. Okay. And so you kind of see what that looks like here in this. Okay. And so this is most common for people with osteoporosis, so kind of the elderly, because again, as we talked about, osteoporosis kind of makes your bones more brittle and it makes it weaker. And so if you take kind of a nasty fall as an older person, you're more likely to kind of injure your hip. right, so next is contusions. And so contusions is another word for just a bruise. Okay. So the front side of your thigh, just by nature of the way that we walk, your thigh is kind of always just kind of bumping into things. And so if you ever had kind of a dead leg before, you probably have experienced this. Okay. And so whenever you have a contusion, that just causes some kind of internal bleeding and muscle tissue damage. But most times these just kind of heal on their own. They're just kind of painful in the injury. And so the other probably most common injury at the hip are hamstring strains. And so these are kind of muscle injuries or muscle damage to your hamstring muscles, which are on the back of your thigh. Okay. And so these can occur, whenever you have hip flexion and knee extension at the same time. So basically when you're kind of like kicking upwards like this. Okay. And so I can kind of feel it because my hamstrings have been tight my entire life. So by doing this motion, I can feel my hamstrings kind of crying out in pain. So and so if you're not a particularly flexible person and you kind of do this kind of very suddenly without stretching, then you can cause some injuries in your hamstrings. Okay? So that's why they say that it's always very important. I mean, it's important to kind of stretch before you exercise in general, just so that your muscles are kind of limber and they can kind of stretch and they're not going to tear on themselves. But that's especially important for the hamstrings, just because of how important they are, for locomotion, for walking, and for doing all kinds of things. Okay. And kind of the annoying thing about hamstring strains too is that because the hamstrings are kind of such an important muscle for just moving around and just kind of moving your legs in general, it can be very difficult to heal a hamstring injury just because in order to heal any kind of tissue, the best thing is always to be kind of immobilize it to kind of prevent it from moving, agitating itself. But that's just so hard to do with hamstring because of just based on just the pivotal role it kind of plays in just a lot of motion that your body does. All right, any questions on these? Okay, so let's talk about the knee and the lower leg. Okay, and so knee injuries are something that's very common. And so we kind of talked about these, and so we have kind of injuries to all the different kind of ligaments in your knee. And so probably the most devastating injury that you can have is an ACL injury. And so the ACL, remember, is kind of one of those interior ligaments inside your knee. It kind of crosses over the PCL. And it mainly is that, and if you have an injured ACL, it becomes very easy to kind of, for your lower leg to kind of push forward. So there's nothing kind of holding it. Okay. The interesting thing about ACL injuries is that when you see kind of people hurt their ACL, it's typically what's called a non-contact incident. So you don't have someone that's actually kind of hitting you from the outside. It's just that you're just the way that your foot is planted and the way that you're kind of pushing off of it, or maybe the way that your muscles are acting on the knee at that given time. That's usually what causes the injury. So ACL injuries are pretty kind of devastating. If you hurt your ACL, you're going to be out for quite a while. So it's very hard for the body to kind of heal that area of your body. Okay. Next we have PCL injuries. So PCL, remember, is the posterior cruciate ligament, and so it's kind of the conjugate ligament to the ACL. And so the PCL prevents kind of backwards motion, so backwards motion of your lower leg relative to your knee. Okay. And so this can occur when your knee is either is hyperextended and when your foot is kind of planted into the ground or plantar flexed. Okay. Not nearly as common as the ACL injuries, but it can occur. And kind of very similar to the ACL, it's very difficult for your body to kind of fix that or repair that tissue, just because that area just doesn't get a lot of blood flow, doesn't get a lot of attention. The other kind of common injury that can occur is an MCL injury. So remember, the MCL is the ligament that kind of runs kind of on the exterior of your knee, kind of on the inside, surface. Okay. And so the image that I have here, so this is a running back in football. And you can see he's sustaining kind of a very large force from the outside. So this guy is tackling him. It's causing a very, very large force, in this direction. Okay. And so when you sustain kind of a large kind of external force on the knee, it kind of causes your knee to kind of buckle inwards. And if that force is kind of big enough, it can cause some injuries. It can cause an injury, or even worse, a tear of the MCL. Okay. And so I don't actually recall if this player got hurt in this picture, but it was kind of a good example of what could happen for an MCL. Okay. All right, and then finally we have the meniscus. So the meniscus, remember, is that kind of almost kind of like cushion that's at the bottom of the knee joint. Okay. And then what can happen sometimes that the MCL can kind of pull on that meniscus too hard, and then it can kind of actually tear off some of the tissue, which can kind of lead to pain and discomfort in the knee. Okay. All right. Any questions on these? Okay. And so another type of injury that can occur at the knee is besides the ligaments, is you can either have overuse injuries or you can have some injuries to the patella. Okay. And so overuse injuries are, just like kind of the name describes, these are injuries that can occur at the knee when you kind of use that joint kind of a little bit too much. Okay. And so one very common example of this is something called breaststroker's knee, where your MCL can kind of sustain kind of almost like a fatigue type injury. Okay. And so if you've ever done the breaststroke, when you're swimming, you'll know that you kind of kick out your legs in kind of an extreme way. You kind of bring them inwards very quickly, and that's what kind of gives you propulsion in the water to kind of propel you forward. But that motion of kind of bringing your leg inward puts a lot of stress on the MCL. And so what can happen is that if you kind of do this kind of excessively without a sufficient rest, then you can kind of hurt the MCL. You might tear it in kind of the worst cases, but it's going to cause a lot of pain and discomfort. And so another common type of overuse injury is shin splints, and so that may be a term that you've heard before. And so the shin splints are kind of pain in the lower leg, which is caused by kind of micro damage, of the tibia. That's a type of bone. So it's tibia is a bone. Okay. All right, and then another common injury is patellofemoral pain syndrome. So that's when you have kind of a painful patella, and so the kneecap, starts to get pain or give you pain or discomfort. Okay. And so this is something that's still kind of unknown because the patella actually doesn't participate that much in motion. It actually doesn't even participate much in weight bearing too. And so the fact that people can develop injuries here in terms of the tendons and the joints and stuff is still kind of a mystery. So some scientists are still kind of studying this, studying it. All right, any questions on this? Okay. All right. Oh, question in the chat. Question. So, isn't it recommended to swim to help knee pain? Yeah, it is. And so, swimming, the one benefit that swimming has is that it alleviates kind of the weight bearing, for your whole lower body in general. Because when you're swimming, you're not really kind of putting weight on your legs. And so, for those people that have kind of painful joints or painful, painful bones, painful muscles, then swimming is a great way to kind of rehab from those injuries. But for the breaststroker's knee, in particular, I'm talking about kind of this particular motion right here, which kind of puts a lot of stress on your inner knee, kind of this area right here. And that's just purely from the motion. So if you're swimming to kind of rehab from injury, or you're swimming to kind of alleviate stress from the lower body, usually you're not going to be doing kind of a motion like this, because this this kind of puts a lot of stress on that knee. Yeah. And so you're probably going to be doing some other things like maybe aerobics, or maybe freestyle swimming, or kicking on a kickboard, something like that. Or probably even better, you're probably going to do a variety of different exercises where you may incorporate the breaststroke, but you're not going to use it so much that it's going to fatigue out the MCL. So it's just kind of everything in moderation, just like those things. Yeah. Okay, and then finally we have injuries at the ankle, okay, or the foot, right? And so let's talk about ankle sprains first. And so probably everyone sprained their ankle at some point in their life, right? And so an ankle sprain happens when you kind of twist your ankle, kind of, or you kind of you bend your ankle kind of way too much that your ankle can actually handle. Okay. And so what happens in those cases, that the ligaments surrounding your ankle or the tendons surrounding your ankle, they either get stretched, or they may tear, maybe just a micro tear. Okay. And that causes a lot of pain and swelling, and you can't really stand on the ankle. Okay. And so the most common type of injuries is kind of when you roll your ankle kind of inwards, And that kind of injures the ligaments on kind of the exterior of your ankle. So these ligaments right here, and the ones that kind of stabilize your ankle from the outside, those are the ones that are kind of most commonly injured. Okay, it is possible to injure the ligaments on the inside of your ankle, but they're just kind of based on the way that most people don't really turn their ankles to the outside. Those are a lot less common. Okay. And kind of the thing with the ankle sprains, that kind of as if you kind of sprain your ankle a lot throughout your life, like myself, the ligaments in that area actually become weaker and kind of they kind of stretch a bit more, and so it actually kind of makes you more susceptible to injuries. Again, so I haven't sprained my ankle. Actually, I haven't sprained my ankle in probably maybe 4 or 5 years, on wood, but growing up playing, because I played a lot of basketball, played a lot of soccer growing up, so like at least maybe like once or twice a year, so I sprained my ankle to some degree. Okay, so we also have overuse injuries, just like at the knee, and so the primary ligament the primary tendon that's at risk for overuse injuries is your Achilles tendon. Okay, and so you may rupture your Achilles due to kind of overuse. And another common injury that occurs from overuse is the plantar fasciitis. So that can cause that's basically causes micro damage, kind of inflammation of the tissues surrounding your ankle and surrounding your foot. All right, and then the final injury that we'll talk about is something that's more rare, but like we mentioned, your tibia and your fibula and your foot bones, they don't really kind of combine all that well. So for most people, it's not an issue just because your ankles kind of your ankle ligaments kind of stabilize it, but you may have kind of a certain anatomy where you may have some alignment issues that cause you some kind of pain, because it puts a lot of strain on kind of the ligament tendons in that case. Okay. All right, any final questions on this? I think that's the last one. Sure. Okay, all right, so that's all we got time for today. We're a little bit early. Okay, so I'll get you guys with extra practice problems, either hopefully this evening, if not by tomorrow morning. So when we come back on Monday, we're going to start another unit on spine. So we're going to start to talk about spinal biomechanics, but spine is not going to be on the midterm. So this moment right here, 5:07 on Wednesday, September 27th. That's the cutoff for the first week. Nothing I said after that. All right, so thank you guys for coming today. I hope you guys enjoy the rest of your evening. Hope you guys enjoy your weekend, and I will see you guys next week. Thank you, Professor. Yeah, you guys. We basically just repeated the stuff that was on Monday, and so basically midterm be in person. Those things that you can bring, you can bring writing utensil, you can bring calculator, and one sheet of notes, so front and back. And in terms of material for the midterm for study, I have a study guide that's posted on Canvas. It should be one of the files there. I posted the midterm from last year, so you kind of take a look at that. And the practice problems, I would start with the homeworks. Okay, homework 2, homework 3, and then I'm going to post some additional practice problems. Probably either if I can get to it now, I can, and if not by tomorrow.
That's trying to do that.
Yeah. All right.
Thank you.
So,
We tried solving last year. We just want to know whether his equations are correct.
Okay. Let me. Can you scan that and kind of send it to me by email? Then I can kind of, because I don't have the solution.
Okay, no problem. I will email you.
Okay.
Yeah.
Sounds good.
Thank you.
Yeah.
be the midterm, like we have to pay, bring sheets and out for writing, or you will?
No, I'll provide all the paper, and so the
Oh.
only thing you need is just your writing,
Mhm.
writing utensil calculator, and then your sheet of this.
Oh,
Yeah.
Thank
But yeah,
you.
I'll provide all the paper for the exam, and then I'll bring some extra scratch.
Yes,
Yeah.
thank you.
Luis, are you still there? Okay, yeah, so besides from the practice problems, we can definitely start with the homeworks, so that's probably the main thing. For the conceptual questions, I would definitely look at the study guide. So the study guide, you know, if you kind of read the study guide, you know, the way that it's the way that I've kind of formatted it is that, you know, for each kind of conceptual topic, you know, I kind of listed a question there that you can kind of answer. And so if you can kind of confidently answer kind of all the questions on the study guide, then you're going to be in great shape for the exam. So I almost never, you know, I never take the study guide questions exactly, but you know, if you kind of can answer everything there and you kind of, you know, can really kind of understand your answer, then you're going to be fully prepared for the exam. So what I usually do for this conceptual questions is that I look at the study guide, or have the study guide open on one screen, and then I kind of, you know, write a question that's kind of maybe the intersection of two questions on the study guide, or maybe one of the study guide questions just kind of worded in a different way. And so, you know, doing the study guide is kind of the best way to prepare for the conceptual part. And then, yeah, and then just for the problem solving questions, just doing as many practice problems as you can, do the 2 homeworks, do the practice midterm that I posted online. And then I'm going to post a few more questions, maybe 2 or 3 more questions today or tomorrow morning. So if you do all those, and you know, and for the homework problems, I always tell people that, you know, I think what people sometimes do is that they do a homework, and when they're kind of redoing a homework problem, they have the solution to the homework problem kind of right next to them, and they kind of just, you know, look at the solution as they're redoing the problem. So so that's not that helpful, because you know, you kind of almost like trick yourself into thinking that you kind of understand everything. Kind of the best way to kind of redo the homework problems is to kind of, you know, turn the solutions over, or kind of, you know, block them out, and then try to do the entire problem, you know, from start to finish, and then afterwards check your solution, just so that you kind of get into that, you kind of get your mind into that mindset of, you know, like you're not going to have the solution as a crutch. You kind of have to figure out everything on your own, which is exactly what's going to happen on the midterm exam. Does that
Thank
make,
you. That was
sense?
helpful.
Lewis, Victor, any final questions before I wrap up the Zoom call? Okay, all right, so I'll see you guys next week. I hope you guys have a good weekend.